All right, so we're moving from a geometric to an algebraic way of adding our vectors together. So instead of adding them by drawing like this, we're going to be looking at the components specifically. You'll notice here, if I have vector v and vector u as these generic vectors here, a, b, and c, d, when I add the two vectors together, I'm going to add the horizontal components, and I'm going to add the vertical components together. And if you think about it, it makes sense to do this. One vector is telling me to move A horizontally. The next one's telling me to move C horizontally. So if I'm going to put those two vectors together, I'm going to have to do both of those, right? So I'm going to move A and then C, or C and then A, right? Depending on which order that I'm adding them in, okay? Same thing with the vertical. One is telling me to go up or down a certain distance. The other one's telling me to go up or down. So I'm going to put those together. Find out what the result is. Now, before we get to an actual example of this, I want to look at these two that I have here. You'll notice u plus v technically would be c plus a and d plus b because I had u coming first, so the c and d have to come first, right? When I do v plus u, the components of v are a and b, so those ones come first. However, these are just real numbers, right? So does it matter which order they're in? No. Okay? Now, we talked about this when we were looking at geometric representation of vectors. I could add v and then u, or I could add u and then v, and I still end up with the same result. That's my resultant vector, right? So I get the same result either way, and we said that that showed the commutative property. Well, here, if we use the properties of real numbers to say, okay, well, if these are real numbers, then that's okay if I put it as a plus c, and it's okay if I write that as b plus d, then I've now proven that those are the same. Okay? So if I were actually trying to prove vector addition was commutative, I would do that. Okay? Something like that. Just drawing it like we did before wouldn't be good enough for a proof. Alright? So those of you going into a math field in college, if you take upper level math, like maybe a linear algebra or an abstract algebra, you're going to be proving things about things that aren't just real numbers, like vectors or matrices or whatever. And this is the type of thing that you might do to prove it. You would state a couple of vectors just in generic terms, not using specific examples, and then you would see what happens and show that they end up giving the same values, okay? Or they don't give the same values, right? And that's part of what those studies do, is try to prove things or disprove things in different contexts with different types of mathematical structures like vectors and matrices and all that. All right, so that's a little bit of number theory for you. But let's get into actually using this here. If I wanted to do u plus v, okay, what would I do?
4 plus 1.
Okay, I'll be consistent. I use parentheses over there. So I would do 4 plus 1, and that's going to give me 5 as my horizontal component. And then what do I do? Yeah.
3 plus 6.
Negative 3 plus 6. So that gives me my vertical component of 3. So that's the vector 5, 3. Alright, so that's pretty simple so far, right?
Wait, I just had a question. Like, what is 5, 3? Like,
5, 3 would be our resultant vector. Okay? So, for example, let me get a graph here. I don't even need the quadrants, but that'll do. So basically what we have, vector u, let's say I started here, okay? Vector u was 4, -3, so I go over 4 and down 3. There's vector u, okay? And then vector v was 1, 6. So vector v, I start here and I go to the right 1 and up 1, 2, 3, 4, 5, 6. Okay? So that's a v. Well, the vector u plus v is this vector right here. Okay? So what is that vector? It goes over 1, 2, 3, 4, 5 and up 3. 5, 3. Okay? No, that's fine. And basically the reason why we do this algebraically is because we don't want, or sometimes we can't really get a good drawing of the situation on a grid. So we do it algebraically, and it makes things a little simpler. Alright, so we look at basic vector addition. Now let's look at the constant multiple. Okay, scalar multiplication. Remember, a scalar is just a number. And here we are gonna well, I'll get to that later. So here we have this vector v, which is again ab. If we're going to multiply that vector by some scalar, then we're going to multiply each of the components of that vector by the scalar. Okay? Now when we were multiplying vectors before, we would simply draw another one onto the end of the first one. Okay? So if I had, a u, then if I put another u on the end, that gives me 2 times vector u. So here in this case, if vector v is 2, -6, then if I'm trying to find 4v, I'm going to take the 4 times the 2, and I'm going to take the 4 times the -6 as well. Okay? So that would give me the vector 8, -24. Right? So again, not a really difficult concept, but we're going to start putting things together here in a little bit. All right? Now, one of the things I want to observe here is what this does to our magnitude. Okay? So let's take a moment. Remember from yesterday, we saw that the magnitude was given by applying the Pythagorean theorem, right? Because the horizontal and vertical are perpendicular, so we can use those components, and the magnitude would be like the hypotenuse. So we had the magnitude of v is the square root of a squared plus b squared. So find the magnitudes of both of those. Find the magnitude of v. And how would we do that? Magnitude of v? Okay, the square root of 4 plus the square root of, or plus 36, right?
40.
So that's the square root of 40. What does that simplify to? What?
2 times root 10.
Yeah, 2 times root 10. Because that's 4 times 10. Square root of 4 would be the 2.
You got.
And we got the 4 plus 36.
I got.
Square root of 2 squared plus the negative 6 squared. Notice the negative will cancel out to be a positive. Alright, so now we want to find the magnitude of the 8, negative 24. Okay, we're finding the magnitude of 4 times vector v. So that's going to be the square root of
8.
8 squared, which is 64, plus negative 24 squared, 576.
Yeah, 5.
And that equals,
640.
there we go, 640. What is 640?
8.
8 root 10. Okay? That's 64 times 10. The square root of 64 is where we got the 8 from. The square root of 10 doesn't simplify, so it's 8 root 10. Okay. Any questions about those? Any observation about those? Isabel?
Well, the 4 vector v, that one, it's the same as the vector v, but at the end it was just multiplied by the 4, like by what we chose to.
Exactly. And that's what our property is that we want to look at. Okay? When you multiply a vector by a constant, okay, and find the magnitude of that result, that's going to equal the constant times whatever the magnitude of that vector is. Okay? Now, there is one part here that we want to make sure we clarify, and that is that C is always going to be greater than or equal to 0. Okay? Because if there's a negative, that's not going to impact our magnitude. What's the negative going to impact? The direction. Okay? So we're ignoring the negative. We would just look at the value of that number in front. Okay? Now, this is also a kind of easy one to prove. So let's actually work through this here. If I'm finding the magnitude of C times V, remember we said it was C times A and C times B. That was the vector we got, right? CV is CA, CB. So if I'm finding the magnitude of that, I'm going to take the square root of that CA squared plus the CB squared.
Equals to C squared times A squared plus B squared.
Okay,
That's
C
factor.
squared A squared plus C squared B squared. Can you guys see what we can do with that?
Factor.
Factor, alright? They both have a C squared. So, I'm taking the square root now of C squared times A squared plus B squared. Okay? Now, since this is multiplication, what can I do?
You can factor out. No.
What do you
Just
mean?
godly
Make it
root.
Yes.
You can take it to C squared.
Yeah, we can split this up. we can split it up, take the c squared out and put it in its own radical.
That's what I meant.
Yeah,
Uh-huh,
I
sure.
think that's what you meant. But
Sure.
and then we had the square root of a squared plus b squared, right? So the square root of c squared is just c. And what is this?
A plus B squared.
No, it's not a plus b.
Magnitude.
It's what?
Magnitude.
It's the magnitude of what?
B.
B.
The original v.
Wow.
Okay? So there's our proof. There's our proof. If this is the magnitude of v, if we're multiplying that vector by a constant, we can just multiply the magnitude by a constant. So if I know the magnitude is 10, and I wanted the vector to have a magnitude of 50, I could just take that vector and multiply it by 5 to make it have the magnitude I wanted. Right?
Yeah.
Yeah. If I wanted, if I had a magnitude of 10 and I wanted the magnitude to be 1,
You could multiply it by 1/10.
I could multiply it by 1/10. You'd multiply each component by 1/10. And that would be how we could make a unit vector. If we had a certain direction, you know, the vector 3, 4, that's a direction, but its magnitude equals 5. So if I wanted it to only have a magnitude of 1, I could make it 3/5, 4/5. I could multiply the whole thing by 1/5, and that
It's already good.
has a magnitude,
Of what?
okay, of 1.
How is the magnitude of 1?
Because this, if I did 3 squared plus 4 squared, that'd be 25. So the square root is
5.
5. The magnitude is 5. So based on what we just said, if I take a multiple of that vector, then if I multiply the original magnitude by that same constant, I can figure out the new magnitude. Okay? So, all right. So, we have learned how to add, we've learned how to multiply, and now we can put them together.
Wow.
And we can
Right.
find
Wow.
we can find composites of multiple vectors put together. Here we have 5 different vectors. We have 2 u's and we've got 3 v's but going in the wrong direction. Okay? Because it's minus 3v.
Oh.
So we can look at this as 2u plus a negative 3 times v. Okay? And if we can figure out what both of those are, then we can just put them together. Alright? So coming over here, what would 2u equal?
8. Negative 6.
Yeah, 8, negative 6. A minus 3 times v would equal what?
Negative 3, negative 8.
Yeah, negative 3, negative
18.
18. There we go. So now I can add those together. 8, negative 6, plus the negative 3, negative 18, and that's going to give me the result, 5, negative 24. Okay. Like we saw before,
What?
basically what this is telling us is, alright, if I'm starting, let's say I'm starting right here, I want to go 2 u's, so that's over 4, down 3, so there's 1 u, and then 1, 2, 3, 4, 1, 2, 3, 3. There's another U. And then minus 3v. Well, v is 1, 6, so a minus v would be negative 1, negative 6, right? So, negative 1, 2, 3, 4, 5, 6. Okay. There's a negative v,
And you need to go 3.
and I need 3 of those. So there's my second one, and there's my third one. So what I just found is actually that right there. That's 2u minus 3v. Okay? Which, if you look at 5, negative 24, to get from here to here, we went over 5 and down 24. Okay? But as you can see, drawing, it's a pain. So we don't want to have to bother with that. That's why we do it algebraically.
Do we need to draw a picture during the test?
No, not unless you're asked to. Okay. But I want you guys to relate what you've been doing geometrically and drawing them to what we're doing now algebraically. Okay. All right. Now, once we find this though too, and this is something that drawing it couldn't have told us. Now that we know the components, we can also find the magnitude.
Oh,
All right.
5
So-
square.
25
25 plus
Okay.
So
576 is
Square root of 25 plus 576. Square root of 601, which we figured out was prime,
yeah.
or at least wasn't divisible by anything real reasonable. So, all right, hey, last minute here, I want to mention this. Okay, direction angle. Okay, direction angle is an angle in standard position. I know we're running out of time, but hang with me here. Okay. A and B, to find that angle, we're going to use tangent. Tangent of B over A.
Yeah.
Alright. That'll give us this angle. The key though is look at your components to figure out which quadrant you should be in. Because this obviously, if tangent's positive, you're in first or third quadrant. If tangent is negative, you're in the second or fourth quadrant. Alright? So you'd have to figure that out. Alright? Alright, that'll be good.
Do I have homework today?
Yes, there's some listed, or at least will be listed in a minute on the blog. Bye. $25.
Oh, yeah, me.
Okay, but the vector 3, 3 is gonna go like that, so we know it's this one, not that. Alright, for vector v, this is the vector
And I need to go
3,
to
4. So tangent of our theta would equal a negative 4/3. And the theta, if you put it in your calculator, will be negative 53.1, but 3, negative 4 is that way, so we want fourth quadrant, so that's going to be 360 minus 53.1, which is 306.9 degrees.
Good job.